Hello? Hello? Good afternoon from Nigeria and in China.
Oh, good evening in China. I say, how are you?
I'm fine, I'm fine. I'm fine. How is life over there?
Concerning the money, Monday, Madam will try and get it for you, okay?
No problem, no worry.
Please, exercise patience. I want to get all for you so that I know I'm done.
No problem, no problem.
He went and he told me that, like he sent me a message that the bank had, I think, this network challenge. He said the network was down, so they couldn't work on the transfer. So next week they will work on it for it.
Okay, no problem, no problem. No. So how was the presentations and the that you are trying to do with your in order to get that design?
Oh yeah, it was okay. I have submitted to them. Let me send you the file.
Okay, okay. Hope they will fund the research now.
Quickly. You say?
Hope they will fund the research now.
Charlie, it's not easy. Now I need to do some other things.
Like
I need
what?
to do. Yeah, I'm coming.
Okay, no problem.
Let me. But this one, can't you send a file? I think there was.
Okay, should I make you admin so that you can share screen easily?
Okay, yeah, then make me admin so I can share screen, yeah, quickly.
Please unmute yourself, please. I mistakenly mute you.
Yeah, no problem.
All right. So you are now the host.
Oh, okay, so
Won't charge low. Buying things that charge jumbo one class. Shema le duro sir. Yeah.
can you see my screen?
Yes, I can see your screen now.
Okay, so like I had to just load this for them.
Okay.
Which is the the rotary feeder base, as you can see.
Okay.
Then the hopper, I maintain the same hopper.
Okay.
I built this one, which is the support stand for the rotary feeder base.
Okay, this is the support stand. Okay, I can see it now. This is stand.
Yes. Yeah. Then this is the cyclone with the copper.
It's not showing you. This one is not showing. The new one is not showing. I'm still seeing the stand.
Oh, really?
Yes.
This is the stand. Hello?
Hello, the stand is still the one showing.
Oh, really?
Yeah.
I'm on the last page anyway.
Okay. This is page 3/4. That's what I'm seeing in the PDF. We are using.
Page 3 or 4.
Yes, that was what is showing.
Okay, so this is 4 or 4.
It's still showing 3 and 4.
Oh, really?
Yeah.
Okay. Oh, I don't know why that page is not showing now.
Mm.
Oh, okay. So basically, that is what I built and submitted to the company, because the company is going to build these ones. Okay.
Okay.
We have the rotary feeder, so they are going to build this and put it on. Today, this evening I was working on this SolidWorks model.
Okay.
And I had a challenge.
Okay. You can share your screen. Let me see, so I can walk through it together.
Okay.
So is the company in China there or over back in Ghana?
Yeah, it's a company in China.
Okay, and they need the research work in their production.
No, the kind of system I'm building has to do with a project which that very company is sponsoring. You get it?
Okay.
So what happened is that, like, what is happening is that now, per the research direction, okay, I'm supposed to design the test system, the test bench, okay. I'm supposed to design the test system.
Okay.
Yes, and the test system which I will design, at numerous circumstances, we are supposed to buy everything ourselves, but along the line, what I've realized is that there are some few challenges. So I need them to build these ones for me. And because I need them to build it, I have to build like the models and send to them.
Okay.
So they can build it for me.
Well, success, sir. Good luck.
Okay, so
Okay. All right.
I've shared my screen.
Yes. Yes, it's showing, but it's not showing selections of different work.
Different work.
Yes, Alex Itas 5.
Oh, really?
That's the screen that is showing.
I'm coming now.
Okay. Okay, the cyclone is showing now.
Okay, the cyclone, okay. So I have this, okay, which is a query.
Okay.
Is the coil also showing?
It's showing, the coil is showing.
Okay, so I want to put the coil on the cyclone. I want to assemble them together.
Okay.
And my challenge was that you see the cyclone has a diameter of 600 millimeters, okay?
Okay.
And I made this Coil 620.
600 and what?
20.
20 mm. That's the mean diameter.
Yes. Yes. So that the coil will be around like
The
a cyclone. Yes.
Yeah, I understand.
But when I send it, when I try to do that in SolidWorks, like I'm having challenges with the assembly.
And we actually have not taught you assembly. So we have not started assembly class. We still have like 2 more classes on parts modeling. Sure, you understand me, sir? So,
yes.
But I can do the assembly for you. We'll do it from A to Z now, then send it to you.
Yes.
Because if you send me your file, I won't be able to work on it because it's 2021. Then I have to just do it myself. But it's something we can just walk through it now, and we get it done.
Oh, okay. Like I just wanted it to help me to just put
assemble
that
them together.
So that we can move back to like our normal class. I know this is off the point.
No problem. Let's just go through it now. We'll do it together. Make me host. Let's walk through it. There's no problem.
Okay.
Please, Emma, by room. Shut it down. All right.
Okay.
So, if I know the dimensions of that cyclone?
The dimension of the cyclone is
okay.
The diameter is 600 millimeters.
Okay. At the top, at the bottom, can you just make a sketch that you can picture, that you can show me like this on camera, so I can
that is
quickly get it. Then
yes, that is so. I'm sending it to you on WhatsApp.
No problem. So meanwhile, while we are waiting for that, let me just do the coil.
Oh, okay. So I'll send to you.
So what's the height of that coil?
The height of the coil is 600.
600
millimeters. Yeah.
So I'll make this guy 600. I'm using my easy way.
Yeah, the one you did the other time.
Yes. $600 then. So we said that the diameter is 620. Sure? Yeah. So to make that 620 now, it's just the half of it. If you can really it's the half of it that's supposed to be here. So I'm just do 620 divided by 2. Then the diameter is 20 or what? Or 10?
The diameter is 5.
How much? 20?
5 millimeters. 5 millimeters.
So now I have to do sweep. Just I made mistake. Okay, no problem. Circular sweep. That's the profile. That's the. Where's it giving me this? Ah, Jesus. Uncle Emeka, please let me attend to the light. I don't know why it's giving me this error. Let me check some things. I'm having a lot of Okay, now I know the reason why. There are 2 lines here.
So, okay.
I have some children that came from church to my place. They were just disturbing.
Yeah, worrying you.
They're really affecting me. Seriously.
Oh, really? The light.
No, the children now. And from our center also.
Yeah.
So, how many twists in non-self are we looking at? How many revolutions are we looking at?
28. No, let's make it 20.
To reach that height, see?
Yeah.
So, I think that's it, see?
Okay.
So, let me save it as what?
Okay. Wow.
So, cyclone.
Yeah, maybe quail.
So then I'm just creating a file for it so it will be easy for me.
Okay.
Why 7 then? So we can now move to the new one, which is cyclone. So I'm checking the stuff we sent on.
Yeah.
All right. You have even made it easy. So
I did revolve.
yes, I've seen it. I'm following it now.
Yeah. At least the revolve is working for me.
Don't worry. I'll get it. So I just add relations to make that perfect. 600. Then year to year is 30. Sure. 300. Then here is 36.5. Sure. 30.5. Then the total height is 1900.
Yeah.
Then we need to know the distance from here to here. Let me assume this at length. So let's check 200 and see. Is that okay? And that under is 1095. Yeah, sure.
Yeah.
So it's fully defined now. Then with this, but I'm still considering this. Is it 365 or 35.60?
It's the down portion.
36.5, Abby. Sure.
Where exactly?
This particular one.
It's 109.5.
The one on the top, is it the same dimension?
Your screen is not showing.
My screen is not showing.
Oh, okay. And the one on the top is.
Let me share again. Is it showing now? Is my screen showing now? Is it showing now?
Yeah.
36.5, yes, Shane?
It's 136.5.
Because it was too small. Okay. Something that was blocking my view there. So, yeah. So we can revolve it now.
Okay.
That's that. I think he has a hole inside, Shane.
Yeah.
But there is still some the outlets we need to create, Shane, this way.
The outlet, yes.
No problem. So let's not put anything like a. So we need to create an outlet, Abby, tangential outlet, Shane. So okay, sketch, convert entity. So that's what I did now. Then I'm going to do another circle here. I think it's of the same diameter with the one under, Shane.
Yes, with the one under, the same diameter.
So I'm now going to use a sketch relations now that says that new circle and this new circle make them choroidal. That means that choroidal, let the radius be equal. So I have the two, then done. The next thing is to put it at tangential outlet. Happy? Sure. So what's the dimension of the
500.
Yeah, Shane? 500.
Yeah, 500. Yeah.
Is that big?
Is it?
Is it that big? That means this should be bigger. This diameter should be bigger. If this is that big.
The diameter is 600.
Yeah, Shane. This one, Shane.
Yeah, but when you see, what I did was to.
Okay.
Measure between where you did the revolve.
Yes.
Yes, and the right. I gave the dimension of 300. So when I revolved, you gave me 600 in your.
Yes, it should be now because it was it should be 600 now. It's 600.
Yeah.
Look at what 500 is. 500 is almost covering it up. So what's the length of to this place? What's the length? This length.
The length, yes, is 500.
This length is also 500.
No, this side, no, this one.
Yes.
The one you've dimensioned now, which is 500. No, it should be 160.
This one, the previous one.
Yes, it should be 160. Yeah.
Because I was like, that outlet should not be like that.
Yeah, yes.
Then I will now do extrude now.
Extrude, yes, now 300.
Selected contour. It should reach this place now. So that there will be a single unit. So you can do up to nest or up to a surface. Okay, the reason why it's not giving me up to nest because the direction. So up to nest. So, or I can also do up to a surface. That shape. This is what we are trying to.
Yes, okay.
So I'm expected to have an outlet here and inlet here. Yes, an outlet here.
Yes.
So I will now shell it off. So I will shell by, let's say the thickness of the metal we are using is 2 mm.
Yeah.
So form it. So 2 mm. I will say show preview. Now, because I want an outlet to be here, I will click this surface. And I want an outlet to be here, I will click this surface also.
Yeah.
And that's so. So we have it now.
Mm-hmm.
So that's the cyclone chain. So we can section it to see what we just did.
But you see that?
Can you see the section? Can you see my screen?
Yeah, I can see your screen.
So I just sectioned it.
You see that there is this. Oh, let me turn on my camera. Sorry.
I didn't
see that there's this like what do you call it? Another cylinder inside on from the top.
Okay, that one is not showing now, Abby.
Yeah.
I want it to show where they will actually mount something like an electric motor, share? Or
yes, on top.
No problem. Let's do that. No problem. I understand what you say. Okay. So I'll just do this.
As in the outlet at the top, yeah.
Okay, like a flange.
No, like a vortex. You see that the circle has a vortex.
All right, no problem.
Wait.
I know what to do. Just give me small thing. Offset by up there. This and should be open. Should this shade? Are you talking about this? It's not clear. Can you see my screen?
But this one, it runs through. It runs through a diameter of like it extrudes through a diameter of 550.
550 up, Abby?
Yes. Yes.
No problem. Sketch. Do this.
Yeah.
This convert entity, extrude, and make it 530. Are you talking about this?
No, it goes down.
It goes down inside inside the screen. All right. Something of this nature.
Yeah, but you see, like it's more of like it goes inside. Maybe we can do midway.
Okay, it goes inside and it also comes upward.
It comes on top, yes. So we can do midway, so it can come up and can go down.
This. Can you see my screen now?
Yeah, like this, yeah.
Is it a thin feature or a solid body? Definitely have to be a thin feature.
It's a solid body. We will share the top and down.
Okay, and that's what I'm saying. Is a thin now, like a thickness of 2.
Finally, it should be a thin feature, yeah.
I won't go back to my share again. This is what you mean. Share.
Okay.
All right, let's do this section and check again. Something of this nature, share. Have you seen inside? Can look at another plane this way.
Yeah, exactly.
This, I believe that this is supposed not to be there. Let me show you what's supposed not to be there. This plate here is supposed not to be covered there. It's because of sketching. So let me just remove that.
So it can flow, yes.
Yes. Okay. Let me remove that, then we'll move on. So we just do sketch here, convert entity, and extrude cut.
Okay.
So it's no longer there. We are good to go. So we can confirm that. Have you seen? It's no longer there.
Yeah.
So everywhere is clean. So this is what you want, sir.
Yeah. And
so is to do assembly now, shey? Yes. Then this is my cyclone. Then the next thing to do is to now assemble both of them together. So control new, assemble this. So that's it. So I'll quickly do some. When we get to assembly class, I will show you. I will need to float it first, then make planes, mate planes together, so that our assembly reference points will also be relevant here. When we get to assembly class, I will explain those ones. Top plane. Why I need to do this process? Because it's going to help you in generating your drawings. If the planes were not perfect with the most fixed object, it's going to result in the right plane and the right plane of this. So that the assembly front plane now becomes your front plane of your product.
Okay.
So that's why I did those ones. So we can move on now and now add again, insert components, then the coil in question. So the question is to bring this at the center of this. There are so many ways of doing it. So I can take this line, that center line, and say mate this, that simple line at the center, and mate it to this. And do what? Make it concentric. I believe this is what you want.
So the center line of the coil, okay?
Yes. This is what you want, I believe. But you need it to, let me show you clearly. Let's go closer to it. You need this to move down.
Down, there, yes.
Yeah.
Yes.
To what level? From the top.
So, let's say from the cylinder down. No, down.
We should still go down.
Yes, so that it will stay under the inlet. You see the inlet. I want it to stay under the inlet.
Let's go towards inlet, Abby.
Yes, it should go down the inlet.
I'm coming. This one. Abby?
Exactly. Yes, and be down.
Short the way that it will be touching the inlet. That this should be touching this.
Yes.
Abby, the last ring should touch the inlet.
Should touch, even if it's not touching, it should be under the inlet.
All right, no problem. Let's do it now. No problem.
Okay.
We are here, no while. So I need the top plane. I can use top plane now to do my mating. So this is not assembling. Then I will now mate it to this plane. It will automatically take it up. I will now say not concentric. I need distance mate. So if I check that distance, it's giving me 588 now. So I can make it 600 or 580. 580 will make it close to it, just touching. So it's entering inside. So I can make it 590. Can you see? Can you see my screen? Look at the inlet, look at the last rand and the inlet. So I believe this is something that looks like what you really, really want. This is the inlet now. Is it clear?
Yeah.
This is the inlet and this is the coil.
Oh, okay. So now the coil is not actually touching the cyclone, right?
It's not touching the cyclone by any means. Okay. But the cyclone is inside of it, concentric. Like, look at me on screen now. Just like this is the cyclone now, and this is the coil around it. They were not touching. I will still section it here so that you will see it. Then remain one more thing, if you care to put it. This guy now can still rotate around it, but it cannot go down or goes up.
Yeah.
But it can rotate around it. So if you want this point now to be at a particular point, maybe facing where your electrical connections will actually be now, we can actually put that last constraint.
Yes.
If you want it, like
Okay.
But it's not really important. Like this face, this is what I mean. Can you see my screen? This face, where this face ties to this face. So I can make this face. Let me just do this. Don't worry. Make it parallel to a particular face.
Yeah.
It should be parallel to this face. Then that's it. So
Okay.
So if we want to section it so that you can see that they are not touching. So I will do this is the image you sent to me in the earlier on.
Yes. Yes.
So this is the image you sent to me.
Yeah.
So I understand that is what you want to do. I perfectly understand that this is what it should look like. So I'm going to see the file on.
Now what I want to do is I want to import this into ANSYS, okay?
Okay, so that you can do the necessary flows.
So I can do the analysis, yes, by the heat transfer from the coil to.
I'm with you. Should I do something like that here?
Can that be done here?
It can be done here. So flow simulations, then let's set up the studies here. Wizard. Okay, it says I should save it before I can do flow simulations. Like I should save the assembly. So let's just complete cyclone.
Can we, is it appropriate to maybe give it different colors, like the coil color and the cyclone color?
Of course, it's possible. Let's do that. I've actually thought in that way. So this one, you want it in which color?
The coil is in copper. Let's say copper color.
Okay, so the cyclone should be what? Blue or what color?
Carbon steel, so blue, yeah, it's okay.
So this is fine, or this? This color? Are you okay?
It's okay. Yeah, it's okay.
All right, then this one is copper, shey?
Yeah.
Okay. That's not copper. That's it, shey? No, this should be copper. So that's it.
But you see, in the afternoon, I saw a video where the person gave a cyclone material carbon steel.
I can do that also. Don't worry. I'll teach you now. Don't worry at all.
Okay.
That's not hard at all. So let's go back to the material. This is it. Yeah. This is the cyclone. Just look at me very well. It's everything I will still teach you along the line. But if I forgot, you can just, these are real life practical. You see where material is?
Yes.
Please sensor, annotations, material, not specified. Yeah. So you just right click on it and it gives you edit the material.
Material, yeah.
So you should show you, this is, this libraries changes. These are one of the things that changes from SolidWorks version along the line. Because if there's any material you discover, this is actually where you put it. If I'm going to teach materials at all, it's a lot of things to touch there, because you can create a custom materials. Let me, this guy, just keep quiet now. What's your problem now? So let me quickly talk to you a little about that. Now, paraventure, we did an experiment. Let's say there's this part of mechanical engineering, there's material. Discovery, material science in Nigeria. We call it material science in Nigeria. So what they do basically, let's say we are doing like a carbon reinforced polyester resin now. We try to take a polyester and we put a carbon fibers in there, then we form the new material. And we want to import that material to SolidWorks. Let's say I want to make an art. For example, this is when I have to do this. When I was in school, we want to produce an art used by engineers in the field. So we had a challenge that we want to simulate what that will give us on SolidWorks. So what we simply do is to produce a sample, just a test sample of that material. So we took this test sample to the lab. then confirm its tensile strength, its ultimate tensile strength, all those things. So if you create such material and you want to use that exact material to run a simulation on SolidWorks, what you will do is to do something called custom materials. So in custom materials now, you will be permitted to put all the properties of that materials there for yourself. So let's take, we are looking at my steel, the carbon steel now, Shay. So carbon steel, we have 1023 carbon steel. We have an stainless steel, iron-based superalloy. These are all carbon steel. So which one specifically are you using for this work? Which are you using specifically for this work?
Carbon steel.
Plain carbon steel, Shay. So
plain carbon steel.
Now this tells us some things. Let me take my time and explain. The very first tab here is called properties tab for material. We are now in material world generally now. This is the elastic modulus of that particular of the material, and it's giving you in Newton per meter square. This is the Poisson ratio that talks about the lateral changes to longitudinal changes. Then shear modulus, mass density, then tensile strength, compressive strength, if it exists, yield strength. You know why SolidWorks have to do this? There's no analysis you want to run, any simulation you want to run, you must put materials. Because it was on this basis, it will be evaluating all the equations. Because it needs this parameter certain time, specific heat, thermal conductivity. So sometimes some things you went online to go and get, they are already in your SolidWorks. Like thermal conductivity of a plain carbon steel now is 43. 43 watt per meter per kg. So then the next thing is the appearance. This is actually how it looks like in real life. You can see. This is the appearance of a plain carbon steel in real life. Cross hatch. So if we are hashing it, this is how it will look like. Custom here, they put a financial impact here. This look like this price for 1 kg when we are running SolidWorks cost. When we are running SolidWorks cost, so we can actually generate the cost of this material. Then applications data, favorites, all those things. Favorite actually talks about which are the materials I used currently, often, so that I don't need to come back to this place to select those materials. So once I'm done with that, I'll just click apply under here. Apply. Apply means that I'm applying plain carbon steel materials for that cycling. For the cyclone. That's what it is. Once you are done, then you close it. You see, its color has changed to plain carbon steel, everything has take order just by doing that. So then you saved it. This is totally different from the color here. You know why? You can actually have a plain carbon steel and paint it this color. The color I gave here was the color of a paint. Not the color of the material itself. So so let's go back to the coil and input the properties. There's no way I will actually
so now it means that even now with this color, which is the blue, okay?
Yes.
Once we have applied and saved the material, automatically it has reflected on the surface. Or it
has reflected on the material. So just like the paint color, that's ash now. So
okay.
I can't even run the analysis. It will definitely ask me to put the material properties I'm talking about. Copper. Copper. Yes, before I can run any copper alloys. So so here we have a lot of copper. Let me help you with appearance so that we can easily. So if you see the one that look like, okay, this is pure copper. Should we just use pure copper? Chrome copper. It should be something around this.
Copper. Just copper.
I should just use pure copper. So if you need to know properties of copper, they were also here. All of them. If you have a very high thermal conductivity, 390, yes, and specifically. So it's very high. So we applied it there. Then we close. So yes.
And these values too, if you want to change it, you can custom your own here.
Yes, you can custom your own there. So should we go through creating a new materials of our own and customing it?
Oh, no, it's okay. Like, I just want to, if we
So
have to custom it, we can do
yes,
that.
we can. Yes, but we can also. I can also teach you now so that we'll just do it together and know
Once and
that.
for all. Sure.
So let's go to edit materials again. So the easiest way to do it, is to look at a material close to the material you want to custom.
Yeah.
We want to take a material of a new copper now. So what you do is you right click on it and you copy it. You copy that material. So you now go to custom materials now. You can create a new category if you want. So new category. So you can call it my material. So inside my material now, you will now paste the copper you are bringing in now. You see now, it's now under my material. So this now, I can do whatsoever I want to change here. So, so if its own density is 3890, not of 8900, so I've changed it now. So, or if I want it at 89, but if you want to change it over there, it will not allow you to change it.
Unless you create and you copy.
Yes, unless you make it a custom property. So now I can apply this now and make its name new copper.
Okay.
So it's my material. I'm the one that knows. Yes.
Yeah.
I'm the one that knows whatsoever that is his property. You see, it's T89. You see this. You see that. That makes it what I want to.
Okay.
So I believe we can move on. Sure. So save this then. All right. So wizard. I just want to show you how to set up flow simulations on solid work. We might not really the whole thing. So, what's the name of your project? Cyclone analysis, something of that.
Yeah.
So, then we'll move to the next one. So, which unit are you interested in using? This is what talks about SI unit predefined. So,
SI unit,
so this is so. These are all the properties you can find in simulations. Everything is there. So we move to next. So is it an internal flow or an external flow? This becomes, please, can you keep quiet? Hello, so is it an internal flow or an external flow? I think this should be an internal flow because we're actually checking something that is flowing inside the cyclone. So it's an internal flow.
Inside the cyclone, yeah.
So it's an internal flow. But this internal flow, does it involve its conduction in solid, which I believe? So you will take it.
Yeah.
So is it saying that its conduction is solid only? No. Its conduction is solid and in fluid also, because fluids have to come inside there and move.
Exactly.
So you will take this second one. Radiations. It doesn't involve any radiations, time dependent, gravity, rotations. If there is any parameter that you feel that is necessary, then you select it. Then you move to the next one. So here is when you actually define the project fluid that you are looking at. Is it a gas? Is it a liquid? Is it a regas? Is it a steam? Or is it a new material that you want to add? You add it. So what type of gases is flowing? Is it air?
Oh, gas, air.
So if I take it like this now, it has put air as my project fluid. You can see these are fluids that exist in this world. Carbon dioxide, ammonia, chlorine, H2O, that's water, hydrogen, krypton, all of this. Now he has to put them because he needs their properties to evaluate the Navier-Stokes equations. So there's no way to do it. So the liquids that exist in the world are acetone, ammonia, R312. These are refrigerants. No compulsory. All this now you will input it in there. So So then next, so what are the solid materials in this question now is actually copper and
the carbon, yeah.
Carbon. So let's look for
Okay.
metals first. So okay, solid in the model. You actually put it, the solid in the model is the copper and plain carbon steel, which is coil 1 and cyclone 1.
Okay.
So please select the solid, okay. So then I think next, I'm not finding carbon steel. So you said you cannot find it there, but I can add anyone that I want to. Is it an adiabatic war? This boys or a word that assumes that there is no heat
transfer. Heat transfer.
It definitely have heat transient coefficient.
Let's make it. Do we have isentropic?
Heat generation rate, surface heat generation rate, water temperature, heat transient coefficient. I think heat transient coefficient should be the next.
Heat transfer, yeah, coefficient, yeah.
So then we can now add that to this. So I believe that value should not be 0. Let's just put 350, for example.
Okay.
Then temperature of the external fluid. Then we keep moving. Then we'll finish all these. Now you just set up the flow simulation. This is not the end.
Yeah.
Now creating lead. So please let me just beat this boy. Let me give them one stroke. Sorry, sir. So now heat transfer. I'm back. Simulations in flow simulations in SolidWorks involve something called creation of leads. Now, what is lead? Those openings, because fluid are coming in and are growing out there, so we have to create leads there. Like a covering is an imaginary covers that will. So here now we'll put a lead there. So here also there's an opening here. Also, we put a lead there.
Yeah.
And here also, we put a lead there. I will still show you.
You just select.
Yes, I just select. We'll create it by itself. Now, why did we need this? We need this because we need to apply boundary conditions.
Yeah.
To all these locations. This is just pure heat transfer, fluid mechanics. If there's anybody that doesn't really know heat transfer and fluid mechanics before, he can't do this. That's just the truth.
Yeah.
That's where the whole engineering thing is really comes in, because it's not just so solid materials in this computational fluid domain. Okay, it means that I'm going to be running Navier-Stokes equations for this area. So that region is where it's going to be running. If you want to see any effect of fluid flows greater than these locations now, you just have to make your domain a bit bigger. Let's say you are interested in what happens before it hits this place. So you have to say, okay, sub-Navier-Stokes for this area, for this entire region. That's what it simply means. So you can increase your CFD area by doing this. But the more you increase that space, the larger time it takes for your system to compute the whole result. So it's more better in a very simple way to just
get it closer.
So what SolidWorks will do basically is that it will automatically generate as closer as possible for itself. Before I adjusted it that time, he has looked into the fluid domain by itself and said, okay, these are your region at which things happen. Fluid subdomain. Fluid subdomain simply means that what are the regions where the fluid in questions will be? We know that inside that cyclone is air, pure air. We can actually introduce particles there. Those ones are advanced flow simulations. So it's fluid domains. Let's just imagine that it's only air that is there for now.
Okay.
So now you have to create the air inside. Now I want to put air inside the cyclone. So how I will do this is to actually look at this and do right click and select order. So from that face downward, you see, let's see what happened on my screen now. All that place, SolidWorks know that there is an empty space inside that. At the moment I create the face, it filled the whole cyclone with air. And what is the gas? You know, we have specified the gas in this study before.
Yeah.
Just follow my mouse. I just create the face of a cyclone. Said inside this chamber, fill it with air. But we have select a fluid type we want to use for this study. Somewhere when we are setting it up, and we said that we want to use air as the gas that will be there. And that's why we find it there.
Yeah.
If you want to add another fluid, you can add it. Maybe we are doing a study of maybe mixing reactions, all those things. There is a lot to learn about. So, is this air moving? Flow parameters of this air, if they are moving, if there is any velocity in X, Y, Z directions, you can put it there. What is the properties of this thermodynamic property, which is very important to us now? I might leave it at 0. Now, just imagine that the air is coming in and it's going out, but there is a reserved air inside. I might do that for just this. Thermodynamic property is pressure, temperature, density, temperature, density. Anyone you can specify here. If you study compressible flow, you will discover that there's actually an equation that links all of them together. So if you select and I sort of thought that from thermodynamics point of view, you just need two properties to define a state of a system. So the moment you give two properties, so whether pressure, temperature, or pressure, density, or any two property, any two thermodynamics property is sufficient to calculate the rest, because there is steam table behind the engine that can actually pick all the whole density, all the whole internal energy at this level. So pressure at 101,235 is just an atmospheric pressure. That's what is giving me there. Temperature, this is just as atmospheric. So you can change all these parameters if you wish. So I might just leave it like this. So now inside this cyclone now is air, filled with air. Then I move to the next one, which is solid materials. So this material now, the cyclone itself is made of what? It's made of carbon steel, user defined solid work material, plain carbon steel. So that's there. So you can see now there's a solid material, plain carbon steel added to this study, added to cyclone 1. Then the next thing, which is very important, is now the boundary conditions. So we have to state the boundary conditions. Okay. I believe that the very first boundary condition is the inlet.
Is the inlet, yeah.
So here, I will just say the inlet inside. Let me clean this place up. Clear. Then I'm selecting other phase. Don't worry. When we get to all this now, so of course the air is moving in at a certain velocity. So we can specify inlet mass flow rate, inlet volume flow rate, inlet velocity, inlet Mach number, inlet mass, outlet mass flow rate. These are boundary conditions we can select. So which one did you have? Or should we just
inlet,
one?
Inlet velocity.
Inlet velocity. So inlet velocity is what? Let's say 300 meter per second, sorry. So fully developed flow. I believe you know the difference between a fully developed flow and
I know.
So these are just thermodynamics. So what is the property at the inlet? Let's assume that this temperature is a bit higher or lower. So let's take it at 373 now. That is entering into a cyclone that have a more hotter air than the air coming out from the inlet. So we can do that also. And with this now, we have specified. So we still need two more boundary conditions here. And
the top and the down. The mouth,
Yes. So we'll still go back here and insert another boundary conditions. And this is happening just at this phase, and it's an outlet, mass flow outlet. Let's just say it's flow, or do you have the conditions here? If you go to answer, you are not going to do any other thing than this that I'm doing.
Yes, I think the same.
Yeah, it's the same thing that you are going to do. So, and if you don't, the problem about this system, let me be very sincere with you, that they are GIGO, garbage in, garbage out. Specify the wrong conditions, get the wrong answer. There is nothing. So you just have to,
magic. There's nothing magic.
There's no magic there. Anyhow, if you are not well grounded in normal theories of thermodynamics, fluid mechanics, all these things, there's nothing that person can do. There's nothing that person can do. So outlet mass flow rates, I can just put this as, let's put it 0.1 kilogram per second. I want to make it fast. Then here also, I have another boundary conditions here. That is also going out here. Set another boundary conditions. Select other. Then outlet mass flow rate, outlet velocity. Let me just make it 10 meters per second per venture. So if you are done with selecting all the boundaries, then the next thing, which is very important at this junction, is why are we even doing this study at all? Which is the goal? What did we want to achieve? So we have different type of goal. We have a global goal. We have an equational goal. We have surface goal. We have a point goal. I will explain all these goals one by one. Now, what we are interested in is to actually observe the temperature of the cyclone. That is called the surface goal, because we are looking at the surface and want to see the temperature distribution over the time. As these fluids are coming in and going out and they are interacting with each other and there is heat transfer like this, what happens? That is, if that is our interest, then that is also possible. If there is a point here, if we are interested in a point here, let's say we want to know the velocity of fluid at that point, that's the point goal. Let's say we want to see the Reynolds number inside this flow. Inside this cyclone, that is an equational goal, because we have to write the equation for Reynolds number, or there is another number you are trying to compute. Mark number, any rubbish numbers, not set numbers, all those rubbish numbers in heat transfer, Grashof numbers. So you can put an
the printer numbers,
Yes. So you can put an equation to define it. Then anything you want. Global goal, maybe I just want to look at the whole system now. Global means the whole system here now. Looking at it, I just want to see temperature of the whole system as it moves. So we need to put a goal, insert a goal, a point goal, a surface goal. Let me just do surface goal. And my surface is that this particular surface of the cyclone, what did I want? I want the total pressure, dynamic pressure, temperature. These are things you can look for. Draft number, mass flow rate. So you can look for the minimum, average, or the maximum. So let me just look for temperature changes, only temperature, so that it will not take my time. But you can see torque, force, in X direction, normal forces, total enthalpy, transfer. These are all properties that is possible. Let me see if I can stretch this out a bit. So that you can see all of them. So you can see them. They are also on your laptop. Static pressure, dynamic pressure, total pressure, total temperature, mean radiant temperature, operative temperature, draft number, density. Anyone you want, you can find the property here. Heat fluxes in XY direction, convective heat transfer rate, all those rubbish. They are hot here too. So then I create this. Then the next thing for me to do, if I've done setting up my goals, setting up everything, I can also say, edit the definition of the mesh, which is if I'm making this smaller, then it's going to take a long time for me to do let me just leave the settings it comes with. Then the next thing is to now run the simulations. So I'll say run it with my computer speed. close. It is not possible to calculate the internal tax if there is no mass or volume of the opening, but no pressure inside the boundary conditions. Okay, he said there is no pressure driving the flow. So let's check this inlet velocity. That means I need to add one more boundary conditions, showing that there is a pressure differences from one place to another. Then, so what I would do is to say the first lead is there, then I will say inlet mass flow at 1. Uniform flow. So I think so it's coming in with this pressure and this temperature. I think this should solve this problem. Yes. First, we want to inlet velocity. Okay. Close. We said there's an inlet velocity boundary conditions there. Let me do this. Let's do this. Select order. So this place is open to the ambient, basically.
Yeah.
So it's open to the ambient though. So it's open to environmental pressure.
Environmental pressure.
I think I need to come here. Edit definition. So it's open to the ambient. Yeah. That way, I think I should be done. If the problem here is that if you don't carefully define all the parameters, it will definitely not work. I did a PhD for somebody with, I will show you his work and what he's trying to do. My brother, okay. It wasn't funny.
It was terrible. Eh?
It was terrible. I'm telling you. And the prof in question is an emeritus. I mean, supervisor. We'll be there 5 hours. We'll be on standing like this, and the man will be on sitting. We are analyzing. And the man is very, very good. He's one of the most respected professors in my school there. So he's actually solving it. So if you need to look at this is the total cells, the numbers of cells he has analyzed, this is the fluid, solid, the numbers is on 27, 28 iterations now, trying to find out what the results look like. I think we are looking for minimum temperature for the fluid. That's still not find the answer. That's why it's still saying invalid go for now. You have seen that knowing how to actually model is totally different from knowing how to do analysis. They are entirely two different things in SolidWorks. Not to even talk of different type of SolidWorks that exist in this world. So I think it has found the answer, the results. So you now go under results here. That's find the answer. So under results, there are
how to generate mesh.
Yes, it has done that. It has done all the iterations. Now, if you want to see the mesh, shall I show you? I think I can show mesh here if you want, but chord plots. So I just want to look at front plane. Chord plot is just looking at any plane you can select. Then what are you looking for? You are looking for pressure, you are looking for temperature. Temperature of the solid or temperature of the fluid. Let's look at temperature of the fluid now. So what chord plot will do is that I imagine that at the front plane, I cut the whole thing. That's what chord plot is. So you can actually generate different chord plots and different, so it will now show you the temperature as it varies. So let's just generate it and see what it looks like. So let me see. So this is the plot, and it's showing that the fluid is around 280. You will just have to follow the color. Though there's another way we can edit it and make it a bit, maybe with graph. So this output now, we can use ISO line, we can use vector, we can use a streamline to show our answers. So based on what we want, then we can also run our analysis and show what the result look like. So a lot of things can be done. SY plot actually talks about if I'm looking at what happens along a line now. So along this edge, over the cross-sectional length now. Model X directions, that's what am I looking for? Temperature. So you can see now, so I believe this is clear. So you can see the temperature along that length.
Yeah.
As it rises and it keep going, that's temperature, the overall temperature of the whole system. Then this temperature of the fluid itself, and this is the temperature of the solid. Because I said I want to see all this in the question. It's actually interesting. This same value now, you can exploit it to Excel, where you actually find the data one by one. So you can see it now. So we did a lot of interesting things then to find. I did a lot of simulations in SolidWorks that makes it very interesting and make it. So you can actually do simulation in SolidWorks on a very simple notice. That's what I mean. So I'm going to send you all these files. But you have to, anybody that wants to run simulations, flow trajectory, I think this might be interesting. Let's just look at flow trajectory. This will actually demonstrate for us in real time how the fluid are flowing. So I just want to see how the fluid is flowing in right, or let me use in front plane. So, and I want to be checking that, should we use lines to show it? Then temperature will be showing with it. Overall temperature will be showing with it. Then, so you can see how it actually turns inside the cyclone. How the fluid turns as it comes in, how it turns. Then let me play it. I think it's playable. So play the animations. Coming, hide this. I want to hide every other thing that I have to. Stop. So this is what happens inside. I don't know why it's not showing. So, but basically, this is the cyclone effect that you're actually looking for.
Yeah.
If I take my time to specify all the old studies, and I think this might also be due to the my system capability, because it's supposed to show me how the fluid is actually rotating inside the stuff. I might show you some of the other ones that are generated, but this is the effect that we are looking for, and it's possible. And this is what it's saying also, that we have a very high temperature at the top, a low temperature coming in, and as the temperature is going out to the ambient, it drops this way. This is, you can also follow the temperature line of the flow trajectory. So this is, I believe it's, so you can actually do everything you want to do on ANSYS in SolidWorks. It's possible. It's possible.
Okay.
So I will send you the file. You can also run
Okay.
analysis and confirm them together. And that's it. A lot has been said on the project today. Today is just the class for the project, but no problem.
Yeah.
That's fine.
Yeah.
So it's just about setting out the right stuff you are looking at. I think, is it particle study? So particle studies talks about adding particles to this flow. I think so, yeah. Because there was a time, these things, if you don't keep having challenges to go and research into it again and again, you might forget. That's just the truth. It's not like extrude.
Yeah.
Like once you know extrude, you know extrude. Like these things, we are not using it day in, day out, day in.
Practice, yes, yes.
It's just about constant practicing that makes it. As at then, I can introduce fan, I can introduce a lot of things to the, because it was has those things, different materials.
So let's say I want to introduce dust particles inside the cycle with the air.
So with the air, so what you have to do is to go to particle studies and begin to add new particles. So what's the name of the particle study? So gas, gaseous material, and you begin. Then where does it enter from? Then you begin to work condition. A lot of those things you begin to specify the interjections. See, there are books I can send that talks about flow simulations if you really want to read them up on SolidWorks. Because if I have to do a new flow simulations, peradventure, if I'm taking that job from somebody, I'll have to go and read it. There's no two ways about it because I'm not doing it day in, day out. But like the last one I just did now, analyzing the inertial force on the steam engine. That one just, I have to go and read about, that one is another study entirely called motion studies. So I have to go and look at motion studies, checking all those forces again. With few reading again, I will easily brush it up and know what is to be done. But if you are not doing it day in, day out, you might forget. That's just the truth.
Exactly.
All right. So is there anything we could do today that is still within our, let me check. Let me introduce equations today. I believe we can just do that one so let's talk about equations today. Then. Using equations in SolidWorks, control new at this. It's a very interesting stuff in SolidWorks. I like it very well. I'm very, very interested in teaching it. Now, let's say I want to start my play. And we've once talked about configurations. So, are you with me, sir?
Yeah, I'm following.
So let me call this place 100. So our aim here is to drive these whole features by equations. Our aim here is to drive the whole equations and the whole structures by equations. So in such a way that let this place be 1.5 of the length. We are considering it as a rectangle now. Let it be 1.5 of the length, irrespective of what the length happens to be. Let this be 1.5. So introducing equation in SolidWorks simply means you just press equation, like equate on your keyboard.
Okay, yeah.
Are we together? It seems that you are tired though. Hello. Go and sit down. But it seems that you are sleeping. Or the screen. Hello?
Hello, Isaiah.
Yes, it seems that you are sleeping on the screen, or is the network? Paraventure maybe is the network.
It's a network.
Okay, are we together? Hello? Can you still see my screen? Hello? Hello, can you hear me? Hello? Hello, you have muted yourself. Oh. You have muted your mic. You have muted your mic. You have muted your mic. You have muted your mic.
It's unmuted.
Okay, now, okay, I can hear you. Now, so I'm saying that in order to be able to introduce equations in SolidWorks, let's say, just do a sketch now. We use this sketch to do configuration the other time, if you can remember. So what I want to do is that, let this be a rectangle in such a way that the length, the breadth will be 1.5 times of the length, something of that nature. So I'm trying to introduce a question, and I said this is how to go about it. So that, please, I want you to just follow. So once we come here, let's say I want to make this place times 1.3 of the length. So what I will just make, I will not press, we have been putting figures when we want to put dimensions. I will now put equal to on my keyboard. So equal to equal to this length, Abby. Then what comes in here is the power of Excel times, this is times in Excel. I believe you are very good in Excel. 1.35, for example, times 1.35. So the moment you do that and you click enter, so SolidWorks will definitely calculate what that value is and give you. So we can say let the circle diameter be what? Be half of the very first, of the very first dimension. So divided by the very first one. And that's evaluated to be 50. Okay? Then we'll now do extrude, I'm going somewhere. Extrude also equal to what? You can pick any of these dimensions, and says divided by 5. So by doing this, we drive all this feature by an equation. So such a way, what this is simply saying is that such that if I change this thing to 350, all the parameters will change automatically by themselves.
Changes themselves,
So having configuration now becomes much more easy because you can tie the whole configurations to that single properties, single dimensions that is changing.
So automatically applies to all the other parts,
Yes, because you know what it is, and what is that. The equation can be as high as, I just did the simple one. You can introduce sine functions, trigonometric functions. You can link it to properties. You can link it to anything you want to link it to, provided that that's what you want to link them to. So paraventure, along the way, I made a mistake in defining my equations. Maybe it's supposed to be times 1.5. I put times 1.65. What would I do? Can I edit equations? Yes. So just follow my cursor, history, sensor, equations now. The moment you introduce equation, it will come in here. Then you right click on it to say manage equations. So these are the equations we added. Is my screen still showing? So times 1.35 divided by 2 divided by 5. So I can actually come here and say it's not going to be divided by 5 again, divided by 2. Then it tells you what it evaluates to, what the answer is. So all these equations, this is where you added them. And paraventure, you want to have a single global variable that all of them refer to, you can add it here. So that even the very first one that is called the length can be here. So then you have that as the, click on it. So it just takes orders and changes accordingly. 6 is not thicker because I reduce it from 5 to 2. This is the power of equations in SolidWorks. There's nothing so hard about it. So you can tie a whole lot of parameters, a whole lot of things together to form a particular one. Are they not closing the gap today so that we can still move on?
Oh, maybe 9. It's 3 minutes to 9.
It's 3 minutes to 9. I know.
Yeah.
It's 3 minutes to 9 now. So these are interesting things. I will send you those files on SolidWorks so that you can definitely handle them. Maybe tomorrow we can. At least we are able to do one thing today. Let me check our syllabus.
Exactly.
Our syllabus. I will share it also now. So that
and I'm grateful, at least.
A lot of eyes opening. Don't worry. Should I do you one more favor? I'm going to send you the live recording of this class. So everything I've talked about, simulations, I'm going to send you the recordings so you can download them and read through them and see how we go about it. It's possible. So Zoom is actually used to record this class. So
yeah, Zoom. I've seen that. Yeah, always you record every lecture. It's good. Yeah.
So
at least I can keep them and be going over, especially if I want to do some simple things. I have to I usually go around and run.
So that is possible. Then let me quickly share our class contents. Let's see where we are.
Okay.
What we are yet undone. Share. So okay, the class actually started from day 1. I think we are done with all this. Chamfering and reflecting on features, slots and slot relations, we have done that. Extrude, revolve and revolve core, done. Introductions to SolidWorks sections and plane properties. We have not done this. Section and plane properties, maybe I might do it now. Then sketch, arc, ellipse and polygon, we have not done them. Arc, ellipse and polygon, we have not. Okay, we have done polygon, but we have not done ellipse and arc. Patterning in SolidWorks, we have not done it. Configuration manager and building different configurations, done. Simple shape using wizard, draft, shell, flex, we have not done them. We have a lot. Sketch 2, spline, we have not done spline, we have not done text, we've done convert entities. Move, mirror, copy, we've not done it. Ellipse, spiral, and thread in SolidWorks, we've done that. SolidWorks design library, we've not done it in Toolbox. Multiple sets, complex planes and loft, we've not done. We've done sweep loft, sweep. So we look at, I believe we are making a serious progress.
Headway, yeah, we are making headway, yeah. So this very night, when I'll finish. I have prepared a project file for this.
Okay.
So I don't know if you use Microsoft project.
Yeah.
But you should have it. So I'll send the project file to you. So because that is what I've been using to track whatever you are teaching me to. So I'll send it to you so that you follow it up. Yeah.
No one. All right. No problem. Okay. So I think at this junction we can really call it a day. Tomorrow we'll meet again. Tomorrow.
Yeah.
In Nigeria. All right. Have a nice day. So I'm going to send you those things I designed. And the cyclone and the coils, yeah. I'm going to upload these recordings to YouTube, but it's not going to be general. It's only people that. Did I send my email address? It's not going to enter your email because it's going to be more than, I think, 64 MB. So what we'll do is that I will send it to YouTube, but in that YouTube, it's not everybody that can see it. It's only people that I give the link that can see it. So it's only you that will give the link. Really? Yeah, it's possible. I have a YouTube channel, so I know how to go around all those things. So don't worry. Oh, okay. I want to create a YouTube channel. No problem. We might look at it in another class and see how we. So I'll just put it there so that only you go there and download it so that you can keep using it for whatever you want to use. It's not going to be. But why don't you? No, I say why don't you use the channel to also make money by putting drawings and those stuff? See, it's not that easy. There are drawings. You see my channel today. Don't worry. You see a lot of work, a lot of designs here. People in Nigeria here, and generally people are interested in entertainment.
Yeah.
That's really engineering. If you put a football of C Ronaldo now, Cristiano Ronaldo, or somebody like Sadio Mane or Liverpool, you see a lot of people coming in and
I know.
so
It comes across, but then sometimes you will never know these things. It depends on how you package it. You get it?
Yes.
Because I know people have been teaching SolidWorks over the years, okay? But the issue is when you go online, there are so many things. So if we can look at some of the wonderful things in SolidWorks, which like you are using in this class, I think it will also work. Usually with Facebook, some of the captions and those things, even for example, like we even attract attention.
Yes, I know.
I see some captions on some video. I just go to click it and when I look at it, I say, wow, this people, what's happening? But you realize that at the end of the day, you viewed already. You get it? you viewed already, so whether you like that's what people have been doing now.
But I have plans, Sha. I'm setting up a training center where I will train people physically. So once they are doing the work, I will giving them assignments. They will be doing screen recording, and I do a lot of video editing also. I don't want to start stretching myself. In short, I left welding outside to come and attend to you in this class.
Okay. Oh, okay.
So it's that complex for me sometimes. So there's no time to do all these things. I knew, but there's no time. I'm too involved in a lot of things. But once things are start getting to the right shape they're supposed to be, then I'll be able to create time for a lot of things. And my children are actually doing wonderful in the training center also. Once they keep creating a lot of things like this, I'll be pushing it online. Then to just, I also have a student I'm training on video editing and all these things that they should just come in. So those one will work. Those one will edit the video and they will push it online. Instead of, see, if I want to be here and there everywhere, I'll just keep myself. That's just
I know.
I need to reduce a whole lot of work I'm doing that are not
I get it.
All right, sir. Have a nice day. We'll see you tomorrow.
Okay. Thank you.
Yeah. I'll send you the files on WhatsApp now. Those assemblies and everything on SolidWorks now. Like I also send the class recording via WhatsApp in YouTube, the link. You can download it.
Okay.
Thank you, sir. Good night, sir.
Okay.